to go in. That is the... Everybody in the world touched the pad and it should be used. So I've got the, let's take a little... Morning crew, Andy Mechanic here and welcome to my YouTube channel. Now a few days ago I did a video on testing the stator, which is part of a charging system, using a shunt resistor. Now one of my viewers, Roger, came back to me and said, hey Andy, there's another way you can do that. So you know, traditionally in the industry we would use a milliohm, which are actually quite expensive because the resistance values of those windings and the stators is very, very low, and it's actually been getting lower and lower more recently because these stators have to be able to produce more current, more electrical items on cars and motorcycles and ATVs, fuel injection, cooling fans, that kind of stuff. So it's become increasingly more difficult in a sort of normal workshop to be able to accurately test the resistance of these windings. And you certainly can't do it anymore with a standard multimeter, not possible. And that was demonstrated in the last video. So I came up with a plan of using a shunt resistor, doing a calculation, giving us some results. Pretty accurate, I thought. And then Roger came back as one of the comments, actually put 2 or 3 comments on the video, which were extremely helpful. And he said to me, and it was called a 4-wire Kelvin measurement. I thought, oh, that sounds really complicated. But actually it's not. It's a really simple procedure. And I want to basically perform that on a known bad stator. And the known bad state is this one here, look. Okay. So we'll find out more about what's bad about this later on via the tests, but it does look pretty burnt. You can see there, look. Right. Okay, so what we'll do is we'll do the shunt resistor measurements on this stator, and then we'll do the, what was it called, the 4-wire Kelvin measurement, a different way of measuring it on this stator, and we'll see if the results are pretty similar. Hopefully they should be, and if they are similar, then we know that we're being pretty accurate in the way that we're measuring it. So then we know we can use either test in the future, and we're going to be getting, you know, accurate measurements and making a justified decision as to whether the winding resistance is in spec or outside spec. Outside spec, buy a new one. Inside spec, good to go. Okay, so it's going to be, you're going to need a power supply or a battery. For the first test in the video previously, basically I used a variable power supply and a couple of multimeters. So most people have, you know, can either get their hands on those, borrow them, whatever. The variable power supply, well, we set that at 12 volts on the first test. That was the shunt resistor test. So you could use a battery for that. Not the end of the world. For the Kelvin 4-wire, so the 4-wire Kelvin measurement, you need an ability to control current flow. And we have to set that to 1 amp. So you will need a power supply for that one. So maybe that's a bit more difficult for some people to do, but most workshops will have, or should have, an adjustable output power supply. Anyway, for your interest, it's a glorious, nice and cool Sunday morning. It's about 10 to 8 in the morning, so it's definitely a good time for sums. Here we go. Right, this is my jumble of wires and bits and pieces for this video. So we're just going to pop the stator on this little stud, this bolt, and an insulated spacer, just in the vise, because I hate to see it being dragged around the bench. It's going to damage more of the insulation. So now it's, you know, just going to sit there quite happily. And the dodgy bit that looks a bit burnt is that one there, look. Right, let's get set up. So we'll use the yellow as our live. I haven't got a red one. I never made a red one. Right, so positive output of the power supply And then we need to go on to that little shunt resistor. Now this was the 220 ohm resistor. So pop that on there, make sure there's a good connection, there should be at that. And on this stator, what I've done is I've marked up the 3 field windings. Because we're doing 2 different tests, we need to be able to relate the results of each winding from one test to the other. So it's really important that we actually, have some kind of reference point for each of the 3 wires. So for test 1, and that's going to be the shunt, we'll call that the shunt test. We're going to be testing the voltage. It'll be V2, won't it, on that one, for winding 1, which will be, we'll say that's A to B. Winding 2, which can be A to C, and then winding 3 can be B to C, and that should give us, if I remember rightly, a millivolts reading. Millivolts, there we are, look, stick that in there. Okay, so our first test, winding 1, A to B. Right, so we'll stick the shunt resistor onto A, and then we need a ground, so we use green for ground. And then we'll stick that back onto the back of the power supply. Excellent. Now we can set the voltage just on the screen there. The voltage actually isn't that important on this shunt test. It's the volt drop that's the difference, that's the important bit. Okay, so we're going to need a meter. Get rid of that one, that's spare. And we'll fire up the old power supply. I'll just crank it up to about 12 volts. There we go. Cool. Right, let's turn the meter on. There you go. Right, you can see now. Okay, so we had to measure the resistance across both the shunt resistor, the voltage across the volt drop across the shunt resistor, and then of course the stator winding, which is going to be these 2 crocodile clips here. Okay, so just like the last video, pop that onto there, and we've got 11.48. So we'll stick those readings down this side. So that's V1, that's V2, and that was 11.48 volts. Okay, and now down here, and I wonder if it'll jump to millivolts for us, will it? No, I'm going to set it to millivolts. Excellent. Okay, because we know it's going to be millivolts. Okay, 8.4 millivolts. Right, now the next one is A to C, so we can leave that one on. We need to move the ground to winding C, or wire C should I say. Okay, more measurements. Right, back to volts. Volt drop across the shunt resistor, 11.47. And across the winding will be that one. Oh, hang on, millivolts. It's so annoying, you've got to keep changing it. Right, so millivolts, 7.8. Now the last one is B to C. So we're already on C. So we'll just move the shunt onto there. It's starting to get warm now. Okay. Right, back to volts. Volt drop across the shunt. Yep, what's going on there? Put that in there, look. There we go. 11.45. Right. And last one, millivolts. So from there to there. Hey, that's a lot higher. 15.5. Right. Okay, power supply off. Turn that off as well. Right. So we can disassemble all this now, can't we? Got the results we want. Get rid of that. Right. We've got some readings. So we've got V1 down here and voltage 2 down here. So that's the voltage drop across the shunt resistor, and that's the voltage drop across the actual winding, each of the 3 windings in the stator. Now if you watched the previous video, you'll know the equation for working this out. I'm just going to work these out now to give us all the results, and then we'll do the test doing the, what was it called again? I've terrible memory, haven't I? The 4-wire Kelvin measurement, and then we'll compare those results, and hopefully they should both be about the same. Right, equation V2 0.298 ohms. Right, perfect. I feel like I should be using a whiteboard and marker pens and in front of a big class doing this. Okay, so there's our results for the shunt test, just down here, look, winding 1, winding 2, winding 3. So now we'll do the Kelvin test, which is actually a really simple test, and we don't even need a shunt resistor. All we need to do is have a power supply that we can control the current flow around the circuit with. So I'll rig up an ammeter, put it in series in the circuit, and then adjust the output of the power supply until I get it bang on 1 amp, and that's critical. Once that's done, all I then need to do is get a voltmeter, set it to millivolts, and take the voltage drop reading across each of the 3 windings, just like we did in the first test. Now, whatever the reading is in millivolts is equivalent to a milliohms result. It's dead simple, and I'll explain to you why. Here we go. So, many thanks to Roger Hewison, for providing this extra information. But just to quickly run through the theory behind this test, this Kelvin test, we relate to Ohm's law. Now, with Ohm's law, we know that volts equals amps times resistance. We know that. That's Ohm's law. So therefore, volts divided by the amps equals resistance. We know that. So, if we set the current to 1 amp, then the volts will equal resistance. But it's critical we set it to 1 amp. We've got to be really accurate about that. You can't just, guess it. So, if we get a reading, for example, of 50 millivolts, that just fit on, didn't it? It will be equivalent to 50 milliohms resistance. Easy. Okay, let's get this test done and see if it's going to work. Right, stator is back. Okay, so we need a marker pen, and we need to be able to control current flow, so we'll set one of our multimeters to amps. I won't use the amp clamp because it's not as accurate, to be honest, so I'll set this up. Just there. I reckon you can see that. Yeah, almost. That going to work? Maybe over here somewhere. Yes, perfect. Right, so that meter is going to measure our current flow. Okay, we need some leads, so we'll use the white lead for our power into the circuit. Put that on there, kind of short out. So it's going to go through the meter. I really need to get some little leads that have got clips on the back, but hey, one day. Right, let's get rid of our shunt resistor, don't need that anymore. And basically we need to do the same tests. So winding 1, which is A to B, this is critical now because we've got to keep a reference. Winding 2, which is A to C, and then winding 3, which is B to C. And all we want is a millivolt. Well, basically it's going to give us a millivolt reading down there. Okay, so A to B first of all. So we're coming out of the ammeter onto the yellow wire, and we'll clip onto A. And then we just need to go from B back to the power supply. Okay, so B on there. Back to ground. Cool. Okay, may look a bit messy, but it all sort of does what it's supposed to do. Just tidy that up a bit. Right, now we need a second meter, which we'll use this one. You can see that or not, hopefully. Be good to have it just on a little stand, but it hasn't got a stand, this one. You see that? There we go, you read that, can't you? Cool. Okay. Right, power supply, back it right off, turn it on. We've got to crank up that amp to exactly 1 amp. It's not easy to keep it on. See where that's going to sit. Okay, well the winding is warming up. So that's probably going to drop down to 1, so let's get ready to take a reading. Right, let's get those on there. Okay, there we go, look, 1 amp, and I've got 162.8 millivolts. 162.8. Right, now we need to change the circuit. Okay, so next one is A to C, so we've got to take that one off. Stick it on there. And that's going to take a minute to warm up. It's dropping. Let's see if we can get another reading. Right. Go away, fly. Okay. Almost there. Almost there. Oh, go down, damn you. There we go. Right, 152 millivolts exactly. Right, 152.0. Okay, last one is B to C, so we'll just try to change that across. Cool. And we get ready for that one as well. Oh, we have to crank it up a bit. Okay, here's a point of difference. Okay, let's let it drop. Okay, so when we get down to 1 amp, we'll take a reading. There we go, 300.7 millivolts. 300.7. Right, that's all we need. Power supply off. Get rid of the meters. Wonderful. Okay. Unplug those because I'm terrible for shorting things out. Okay, so our answer here isn't in milliohms, it's in ohms. So we need to transpose that, because that's essentially milliohm reading, isn't it? 162.8 milliohms. We need to transfer that into an ohms reading so we can compare very simply. Winding 1 is going to be 0.1628 ohms. Winding 2 is going to be 0.152 ohms. Winding 3 is going to be 0.3007 ohms. Okay, let's put that onto here. So 0.16, I'm going to round it up now, 3 ohms, 0.152 ohms, 0.301 ohms. Yeah, that's pretty close, isn't it? Oh, and just for reference, the spec is 0.09 to 0.13 ohms for those windings. So, looking at that, all of them are outside spec, so that stator will be a fail anyway. Well, there you go. Pretty damn similar results, to be perfectly honest. We've got the shunt test results down here, and we've got the Kelvin 4-wire test down here, and really there's bugger all between them. Certainly I would class either as being accurate enough method to test the windings in that stator to decide are they inside spec or outside spec, because if they're outside spec it tells you something's not quite right. Maybe some insulation's, you know, broken away from a couple of the windings so that the current's not going around a few of the loops of wire. It's just taking a direct route, which would reduce the resistance in the winding even further. Or maybe there's you know, some of the wire is burnt or partially broken, or you know, and that would increase the resistance of that winding. And on these results, especially on winding 3, which was B to C, that one has got a much higher resistance, almost double the resistance of the other 2 windings, and way above spec. So I thought what we'll do now, because the winding is scrap, is we'll put a current through it without a resistor, and we'll crank that current up, and what should happen is the point of high resistance should get hot. Now we know that winding 3 is the most problematic, so we'll leave that till last. We'll do windings 1, then 2, and then 3, and we'll give it as much current as we can. I'm not going to put, I could put a battery on it, but I'd like to be able to control it, so I just want to be able to wind up the output. Right, so I'm going to set the stator on there because it shouldn't short out on the bench then. This is the crankshaft crank angle sensor, the pickup for the crank. It's all part of the same part. Right, need a couple of wires again. Right, so positive, and winding 1 was A to B, so we'll put that on there, and then we'll go from B back to the power supply. Pretty simple circuit. Okay, we'll turn the power supply on. Let's back it off first. Turn it on. Right, so this was winding 1 that had a resistance of about 0.16. Right, so you can see the damaged area around here, look, mainly that one. Okay, so I'm just going to crank up the current. Right, voltage and amps is now climbing up to about 5 amps. 10 amps. Ooh. Oh, look at that. Now that's cool. Okay, so a bit of smoke. So that's our, oh, and fire. Oh, I like that. It's like a little cooker. Electrics are fun, aren't they? Okay, let's see what we're going to get on one of the other windings. So the power supply is now off, and I'm going to connect that to winding 2, which is A to C. Right, A, oh, crocodile clips are getting hot. A to C. Right, here we go. So I'll leave you guys just down there, I think. You can see a lot more. Okay, so we're on a different winding now. Okay. Up to about 20 amps. Oh yeah, I can see a bit of smoke. Look at that. That is cool. Yeah, right, maximum output on the power supply. You can't quite see that, but it's very cool. Houston, we have a problem. We're melting wires together here, look. Okay, power supply is back up and running, but it looks like we've gone completely open circuit on... oh, there we go, look. Got it back. Bloody good. Okay, so before we completely kill that, let's go on to winding 3, which is B to C. Right, so we'll just move that one across onto B. And let's see what happens. Now, this was the winding with the highest resistance. Now, obviously, with all those, you know, that smoke and stuff and the burning, it may have affected that circuit now, but we just don't know. Give it a go. Just for a bit of fun. So B to C. Here we go. Oh yeah, look at that. The other great thing with these is they're electromagnets when they're turned on. Not particularly strong electromagnets, but they are electromagnets. Now don't forget, normally these are not fed a current. They have a current voltage induced into them by rotating magnets around the flywheel. So as the flywheel spins around, the lines of magnetic flux cut through these wires and induce the current, and they induce an AC voltage into these windings, which then goes off to the rectifier to be converted to DC so you can charge your battery up. But I don't think this one's going to be doing any more charging anymore. Right, okay, I think oh, there we go, perfect. Ooh, flames. So you can imagine, while it's inside the engine and it's got all this current flowing through it, and we're talking 100 to 110 volts AC, this is what's going to be happening as it's having the current induced into it, and that's what causes all the burning on the insulation. There must have been a point of, you know, high resistance, or maybe where the insulation has come off, and eventually it'll burn out. It's pretty cool. And the insulation on these wires is only really, really thin. It's like a varnish almost. That's bizarre. Take the flash off. There you go, look. See a lot better now. Right. Okay. So now, let's hook up a battery and completely destroy it, I reckon. I've had a battery on charge for about 3 days for an MR2, which is I'm going to be working on next. So I've used some jump leads because we're going to have quite a bit of amperage going on here, and it all may happen really quickly. Okay, I'm just going to touch the negative of the jump leads onto the negative of the battery, and I might actually put some eye protection on. Actually, hang on a second, because it could actually could be quite eventful. Okay, here we go. So we've got unlimited amperage supply now, basically. Well, it's got a much deeper into the winding failure there, look. Oh yeah. And we've got some more starting around on this winding here, look, as well. Just see the insulation bubbling away. It's like a little fire starter. Essentially all it is a heating element, isn't it, really? At some point it will fail. It's amazing how much abuse these things can take, isn't it, really? I can actually feel the heat, and I'm about a foot away from it. And there's smoke coming now from pretty much the whole stator. That's getting very hot, as is that one. These are all changing colour. They're not as shiny anymore. I have to charge my battery up again now. I wonder how many amps it's taking. Where's the amp clamp? Oh. 27.4 amps. I reckon the battery can cope with that. Oh well. Maybe I should just leave you to it and I'll go and get a cup of tea. Oh, the current is dropping though. Maybe the battery's going flat. Should cope for a while though. Way! We've got fire! Holy shit. Didn't plan on that. Well, there you go. One very dead stator. Well, I can make fire. This is pretty cool. Well, that overloads it, so what does it go up to when I do that? So that's obviously shorting out two of the circuits. Oh, we've got a broken winding there, look. So that must be one that's not currently in use. And that white flame is probably the insulation burning off. Cool. Okay, well, fun's over. I did wear safety glasses. I was a little bit concerned. Didn't quite know what was going to happen there. But hey, good fun. I don't mind destroying stuff when I know it's already... it's already destroyed. Push that out of the way. That's going to take quite some time to cool down, I think. Stick it on the metal. Right, there we go. Bit of heat transfer. So, yes, workshop did catch fire a little bit, didn't it? But interesting to see, and like I say, it was scrap, so it didn't matter. It's just going to go basically for recycling. Okay, so the question is, and I'm sure you really want to know, before we sign off, what's the link between these windings? Because in reality, when we're testing what we call winding 1, A to B, we're not testing one winding, we're actually testing a pair of windings. They are linked, and there's two different ways that they're linked. And sometimes a 3 winding stator has 4 output wires. Let me explain to you how that works. A lot of car alternators have 4 output wires and not the 3. Motorcycles, they only ever have 3. I've only ever come across 3 output wire stators. I'll do a quick diagram just to show you what I mean. Here we go. Okay, so there's 2 different ways that a stator is wound, and they both have 3 windings. There's the delta. Now the delta, the windings are wired up like this. And they connect like that. So we'd have the 3 output wires, which is what we see. So you'd have A, B, and C. Okay, so imagine it was a delta style stator that we were checking the resistance values on. And we put our meter, if you were using a milliohm meter for example, we put our meter onto A and onto C, and we're going to measure the resistance across there. Okay, that would measure the resistance of this winding, but it would also include the resistance of both these two as well, and we get an overall reading. So we'd have, a single resistor here and then a pair of resistors, in series, and that will give us that result. And the same goes for if we pass a current through that winding, through the stator. If we connected a power supply to A and C, we're going to get current flowing through here. We're also going to get current flowing through here, and that's basically why we saw, even though we're only on one winding, we were seeing smoke and heat being developed at all of the windings, around the outside of the stator. Now the other type is called either 2 different names, a Y connection stator, or in England we call it a star configuration. And with this one, it's like this. Okay, so it's like a Y shape, and again you can have A, B, and C. Now again, if we were to pass a current through A to B, then of course the current flow will be through these 2 windings here. If we were to measure the resistance, then again it would measure the resistance of 2 of the windings. B to C again would measure the overall resistance of this winding and this winding, and that's probably why we're getting such a low reading. Now I mentioned to you also earlier on that some stators have 4 output wires, and basically what happens is there's a common in the middle here and an additional wire comes off, and that's normally found in car alternators and stuff. It's pretty good though, isn't it? 2 different types. And the Y connection, this one, is more commonly used in higher RPM applications like motorcycle engines, and these ones don't produce such high amperage normally. These ones are much better at producing a high amperage output. So there you go. That hopefully will help you to visualize what's really going on. Just bringing the stator back, and it's still pretty hot. We've got here each of the windings going around the stator, and if I was to label those up, let's just say for example that that's 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, burnt one, 2, can't write upside down, 3, 1, 2, 3. There you go, look. So now you can tell that, for example, you know, winding 1, the actual wires themselves, for example, will be on that on that post, that post, that post, that post, and that post. Winding 2, so on. So you get a better idea of what's going on. And as the magnet passes, it's going to induce a current into 1, and then induce a current into 2, and then into 3, depending on obviously the rotation. If it's going that way, it's going to go 1, then 3, then 2. And that's how the current is induced in phase into each of those windings. And the rectifier unit then smooths out those phases, those outputs, to give us a continuous, or almost continuous. It's got a bit of a wave to it, but nothing too serious. So hopefully that's helped you to understand what's really going on in a stator. Okay, well, there is another video that I did when I pulled a car alternator apart. It had a fault, and we did a full internal testing of each of the components: the stator, the rotor windings, the regulator, the rectifier. We measured the brushes. There's quite a few videos on all that kind of stuff, and I go into more depth about how the current is induced into the stator, and basically, you know, how the actual alternator works. So if you're interested, then watch that as well. This one was more to do with that Kelvin, the 4-wire Kelvin measurement. This video, I didn't want to go into too much depth on how the stator actually works. Okay, crew, well, hopefully you found that video interesting. We had multimeters, power supplies, wires, calculations, fire, all sorts of stuff. Oh, and a few diagrams. So there you go. Sunday morning teaching, job done. If you enjoyed it, why not subscribe to the channel? Click on subscribe. You'll see a little gear icon turn up. Click on the gear icon, and then you can tick the box to turn on notifications. And our friends down at YouTube will send you an email as and when I upload any new videos. If you're on a smart device, then just click on the bell, and again, that turns on notifications for you. You'll also find me on Facebook, Instagram, Google+, and Twitter. Feel free to communicate through any of those portals. However, first point of contact, if you don't mind, via the comments on YouTube, because let's face it, that's where the videos are. I can't promise to answer every single comment that you post, but I'll do my very best. All right, crew, cheers, over and out.